Good afternoon. Welcome you all to the final High Performance Architecture webinar series. My name is Lan Ding, Associate Professor at UNSW Built Environment and the convener of High Performance Architecture Research Cluster. Before we begin, I would like to share my respects and acknowledge the Bidjigal people who are the traditional custodians of the land on which this meeting takes place, and to elders past and present. This is 8th High Performance Architecture webinar series this year. The speaker is Dr. Riccardo Paolini, a senior lecturer with the School of Built Environment at UNSW. Dr. Riccardo's research mainly focuses on the performance of buildings and the built environment, considering the energy response and indoor environmental quality in buildings during heat waves and extreme heat in general. Also, he extensively investigated the performance assessment of urban heat mitigation technologies, including aging of cool materials. In today's webinar, Dr. Riccardo will present performance gap in urban heat mitigation. If you have any questions during Dr. Riccardo's talk, please put it in the chat. Dr. Riccardo will answer at the end of his talk. Also, this talk will be recorded. We would appreciate you switch off your video and microphone if you do not wish to be seen in the recording. Riccardo, over to you.
Thank you so much for the introduction, and good afternoon, good morning, or good evening to everyone from wherever you're joining. So our team is research group is high performance architecture. Although we're not all architects, so Matt is a physics system and engineer. Many other colleagues are architects, and indeed there's need for a lot of disciplinary competencies to tackle urban heat mitigation. And many of the talks we had previously were about the physics. And this one is about a little bit more about the engineering side of the problem and the implementation before moving towards the implementation and having it implemented in architecture and in the built environment. So why bothering? Because we have very high temperatures indoors in buildings as a result of urban overheating, but also because of the use of solar reflective materials. So here showing buildings in the Greater Sydney area where indoor temperatures can be as high as 40 degrees during summer because of this. And as a result, when we have very high indoor temperatures, especially during heat waves, we have a mortality peaking in an heat
Excuse
wave.
me.
Yeah. Do you see my slides?
We haven't. Can you share your PPT slides?
I think you have to stop sharing because I shared my screen. But yeah. Okay, I'll go back.
Yeah, we can see it now. We can see it now.
Thanks, Lan. So I was saying we indoors in buildings that do not implement cool materials on the roofing and in an overheated urban environment, we can measure temperatures as hot as 40 degrees during the summer during heat waves in the Greater Sydney, or again very high indoor temperatures in Europe as well. And when we have high indoor temperatures exceeding contributing to a body heat gain, people cannot cool during the heat wave in summer, and we have a peak in mortality. We have many deaths due to heat waves, to extreme heat events, and Also, these are concentrated in where we have most of urban sprawl. So, for instance, in Sydney, in the Western Sydney area, and in the long run, we will have increasing nighttime temperatures as well, even in Australian cities. So, we need to address this problem and find and implement a solution. So a lot of science has been developed, as we saw in previous webinars. So now we have to put it in place. We're all familiar with the building energy performance gap. So we think a building will be zero energy or will have a low energy consumption. So, and there's a sharp difference between expectation and reality. So we have a very low predicted energy consumption, but then the real energy consumption is much higher. Why? Because of geometry, because of physical properties, because of the user's behavior, because of how we represent the physical processes, whether we produce the prediction with an unsuited model. So a lot has been done in that realm. A lot has been done, and we have a lot of information from post-occupancy evaluations in buildings. It is not so when it comes to urban overheating mitigation, for the simple reason that we don't have many large-scale implementation of heat mitigation, and therefore there's not enough post-occupancy evaluation. But there is something, and it is very similar. So we have issues concerning geometry, physical properties, user behavior, and representation in modeling that lead us to a change in the estimation that we have. So, and this is the scope of this talk, to address when, why, and how. So it's worth naming and recalling the heat mitigation technologies. So we have cool surfaces, namely surfaces having high albedo or high solar reflectance and high thermal emittance. These include cool roofs and cool walls and cool pavements. Then we have greenery with street trees, urban parks, and green building envelopes, so green roofs and walls. And then we have water-based technologies, water fountains, ponds, misting, and street watering, and also the reduction of anthropogenic heat emissions. So in this talk, I will focus mostly on performance gaps in the first two, because water-based technologies, mostly the problem is clogging of the nozzles or more mechanical things. Of course, on top of these technologies, we have combinations of green and blue infrastructure, and so on and so forth. The best combinations at the regional scale, when we implement these at regional scale, can deliver 2 to 3 degrees of a temperature reduction maximum. For instance, in Sydney, we saw a maximum of 2.9 degrees with a citywide application. So across the whole greater Sydney area, application of good materials and irrigated greenery. But the average reported literature, and it was a review published a few years ago, was close to 2 degrees in peak reduction, and of course it's not even across the area, as Matt has shown in previous webinars. Another important thing to recall is that when we implement heat mitigation, we also change the planet's boundary layer. And because we are reducing the surface temperatures on, for instance, on the roofing and in the city, therefore we have less turbulent sensible heat, less convection, and therefore we are sucking in less hot air from the surrounding. So it is a very complex phenomenon, and this to say that the performance of heat mitigation interacts with the climate, and therefore we have to consider them all together. This was a recap about mitigation. what is a recap about adaptation? So we have emergency management plans. So we have GPs, civil protection, and volunteers visiting vulnerable population. This was response in Europe right after the 2003 heat wave. That was the first response in the following heat waves. Then heat wave shelters, or cool centers, as they are called in Australia, energy curtailment for non-essential services, and then having air conditioning in buildings, including heat wave shelters, and then we have some semi-active, so with air movement, and also having passive buildings, so adapting to embracing for impact. And here we see what are these aspects of performance gap. We will try to have a look at them one by one. So first one is the planning stage. The planning stage, we might consider more flat roof surface than it's actually available, because we have a lot of pitch roofs, allowing for lower albedo because of color zoning, for instance, because we have HVAC, so we have a lot of machines on rooftops, and we have a lot of PV. That therefore reduces the area available for core roof deployment. And to know this, of course, we need geographic data. We need that information from inventories, and this is not all available. As you can imagine here, it's nearly impossible to have an understanding of how much area of a rooftop it's occupied by machinery, might be cooling towers, or air cooled chillers, or pumps, or sprinkler tanks, or anything, and how much instead is covered by a roof sheeting. So we have two starkly different situation, and we do not have the information from general inventories. So this is one of the roadblocks to have an understanding of the actual performance of a heat mitigation when it comes to implementation. So we need actually more geographic knowledge, and also having an understanding in design that we can favor the application of building services integration, the design of building services integration, so that the implementation of heat mitigation technologies is viable. Another aspect concerning modeling instead is the fact that as yet most standard building energy simulation engines and also mesoscale modeling do not consider the effects of dew on roofing. Especially for core roofing, we have a formation of dew, so condensation on the rooftop, and therefore we have in the early morning a phase changer with the evaporation of the dew, and the standard models that we currently use do not represent this aspect. So this might lead also to a performance gap in the estimation, as we have the performance gap for buildings. Then one of the biggest factors leading to a performance gap in the field is the loss in solar reflectance due to aging, which is predominantly due to the deposition of soot, also known as black carbon, on the rooftop surfaces. So we can have a very, very important effects, and this has to be assessed in the field. Because some aspects cannot, it has to be assessed in the field on the real buildings and with the natural exposure. Because yes, we have methods to have an accelerated practice to mimic and to reproduce the effect of outdoor aging roofing and facade materials, but not all aspects can be represented. For instance, of cleaning, when it comes to photoactive materials or fluorocarbon materials, and when it comes to physical disintegration, so fake self-cleaning, appearance of cleaning, but the material is actually disintegrating, and therefore it restores the initial reflectance, but because chunks or flakes of the material are falling off. Or when we have a combination of multiple degradation agents with a mutual influence on the effects. So and here we see, for instance, a couple of examples. So here we have a waterproofing membrane, polyolefin, exposed for 3 years in Milan, Italy, and without biological growth. And here on the right-hand side, with the biological growth, and we see the difference that in the laboratory exposure cannot represent this. However, the important bit you see here is the substantial loss in reflectance across the spectrum, symptom that it's due to black carbon. And the losses are quite substantial in European urban areas. This is the only study where the exposure has been performed in urban areas. If we have an initial solar reflectance of a roof equal to 80%, after 3 years, 3 years and a half, it drops to 53% in Milan and 63% in Rome. So with an average of 58% stable solar reflectance. So the loss is quite substantial. It's not something that we can forget about when it comes to implementation. I was mentioning that was the only study performed in urban areas. There are for the simple reason that the land use is expensive, and when it comes to deploying an exposure farm for testing of materials, that is definitely a factor. And there are in the US, this the first program that started, the first most relevant program that started with industrial testing. Industrial scale testing is conducted by Co-Roof Rating Council in the US, and after 3 years of exposure, here you see that the reflectance drops in some cases significantly, as you see here. So if the initial is around 0.8, it drops to below 0.5 after 3 years, and this is the average of all the 3 sites used for the exposure in the US, namely in Ohio, nearby Cleveland, in Arizona out of Phoenix, and in Florida out of Miami. And instead, there are also some materials that do not feel the effect very much here. They are almost unaffected by aging. So there are some promising results. However, on average, if the initial albedo is 80%, the age albedo, even here, it's 70%, even in those non-urban sites. These are 2 of the main programs. Again, there's some other evidence from China, Japan, and Brazil, and again, more or less the same trends, but of course the values are different because every site is different. And what we can see here for people listening from Australia is that we don't have anything in Australia at the moment. This is a freshly minted review just published a couple of days ago. So most of the studies are experimental studies. The only program involving industry and continuously run is the one in the United States. That's one being implemented by the European Co-Roofing Council in Europe, but it's at a good stage, but it's not in full operation as yet. And here again, some other examples. As you can see, it changes radically from site to site, even for the same initial solar reflectance, because it largely depends on the product, but also on the environmental conditions. This means that if we don't have information here, we cannot take information from elsewhere. So we cannot just run a computer simulation. We need experimental data. What are the effects of a loss in solar reflectance? That's the surface temperatures increase radically. So if we have a new roofing membrane with a initial solar reflectance of 80% and age solar reflectance of 56%, we see here a substantial increase from 32 to 53 degrees over thermal insulation. And every day the maximum surface temperature is higher than the for the aged membrane than for the unaged membrane. So, and the difference is substantial. So even 20 degrees, consistently 20 degrees hotter during the summer. So it's not just a single day. So what is the impact on urban heat mitigation? There's no specific study on the impact of soiling or performance loss on urban heat mitigation. However, it's quickly done because the temperature reductions due to urban heat mitigation are usually linear with albedo. When it comes to albedo, then with greenery and latent heat exchanges, there's a strong deviation from linearity. But for albedo, it's somewhat linear, not perfectly linear, but we can have an educated guess. So if we take results from our study that Matt presented in previous webinars, we have a conventional roof with albedo of 15% and a cool roof with albedo 85%. And if we deploy the roofs across Sydney, we have a maximum peak reduction of a couple of degrees, and therefore, if we have an albedo loss of 20%, like we saw in the previous papers and from experimental results, let's say from 80% to 60%. In solar reflectance, we have a loss in mitigation of approximately 0.6, 0.7 degrees. Or in other terms, we lose 0.3 degrees in mitigation for every 10% of solar reflectance lost due to aging of materials. That was for roofing. What happens to cool walls? We have less information available than for cool roofs, and we have also a lot of uncertainty due to the window-to-wall ratios in the across urban environments. And natural exposure programs are more recent. So there's one program just started in the US, but there's nothing underway anywhere else. Only research campaigns, as the one shown here, where the initial solar reflectance was 75%, and after 4 years, it was 55%. Aging takes longer for walls because the deposition is typically longer. Again, if we have self-cleaning, we need to run a longer campaign because it's not forever. For walls, especially due to the visual impacts and the influence on the aesthetics, self-cleaning. It's one of the areas where self-cleaning has been implemented the most. However, after aging, the self-cleaning performance decreases because the titanium dioxide, that's the technique that's used to achieve self-cleaning. The titanium dioxide gets deactivated because of clogging the pores or because of alteration of the structure of anatase, and it's not that effective anymore. After cleaning, it recovers a little bit of the initial performance, but not all of it. And that was from an exposure campaign we ran for a couple of years in Italy. Here you can see the effect. So this is a Jubilee Church in Rome that was commissioned in 2003. And in 2018, on the right-hand side, you see what was the effect, because it was not self-cleaning anymore, and it was subject to major degradation. Also, when it comes to flat roofing, natural exposure programs are quite representative. It is when it comes to wall surfaces, the morphology of the facade plays a major role, as you can see here, because it induces differential rain wash, and therefore a substantial difference in the patterns of areas that get rain washed and that can get cleaned by rain. As I said, there's one program that has started in the US, but only a couple of products have been tested, because the exposure program runs for 5 years, because for walls, as I said, the exposure is slower. The aging process is slower. You get to a stable value in more time. But again, similar results with initial albedo. If we take just the products exposed with a high initial albedo, again, we see losses after a couple of years that are in line with that study that I referred before with the natural exposure in Italy. Same story. So what happens for urban heat mitigation? Here we have an example from LA for per 0.1, so 10% wall albedo increase. Cool walls can reduce summer daily average Canadian air temperature by 0.05 degrees, and the peak temperature close to 0.1 degree per 0.1 increase in wall albedo. Therefore, again, we have a mitigation loss of 0.1, 0.2 Celsius degrees for each 0.2 albedo decrease for the walls. For cool pavements, there's no extensive campaign. There are only a few papers. The reason is, of course, you cannot expose the pavement on roof racks and forget about them for a couple of years and then test them again. But you need to measure them in the field, because of what leads to the aging of cool pavements is the torque of the tires, the oil dropped by engines, and the overall pollution in the city and the wear and tear. That is when it comes to cool pavements, there's no general and widespread natural exposure program, but only isolated measurements on single implementations and only very few papers. Aging might reduce the mitigation potential by 25 to 50%. So in these papers, we have from 0.4 to 0.47 to 0.40, or from 0.26 to 0.15. So again, it's less pronounced than, because it starts from a lower reflectance point, but it's still relevant. And there's an ongoing study by ASU in Phoenix from 0.35-ish to 0.2-ish in 7 months. Another factor that is worth mentioning then when it comes to cool pavements, that there's a risk of double counting trees and cool pavements, because they're acting on some of the same heat mitigation mechanism. Namely, cool pavements are mitigating the urban environment because they are reducing the heat gains by reflecting more sunlight, and trees are reflecting a tiny fraction from the top of the crown, but mostly are providing shading. So they are reducing the amount of sunlight that gets to the pavement. So these two factors, these two dynamics are the same. So we risk on double counting them with modeling, and not all modeling tools take that into considerations. So some consideration on aging of cool materials before moving to greenery. So when it comes to service life studies, they often exceed the service life of researchers. So which is the limitation. and also the time span of research funds. And this is one of the reasons why we don't have so many, and therefore industry collaboration is vital to have this information and develop new products that can be deployed and be effective. And laboratory exposure is also only one slice of the story, kind of reproduce everything. So we need data from the field. What I was mentioning before, trees. So trees mitigates the urban environment by reflecting a little bit of sunlight from the top of the crown, mostly, and then a lot by shading the street pavements. So if we have a solar absorptive street pavement, so let's say 5% reflectance, we are reducing the amount of sunlight that gets to this solar absorptive pavement, and which therefore reaches a lower surface temperature. And then the important factors are, of course, transpiration from the plants and evaporation from the soil. So what do we get in terms of heat mitigation when we're using trees? So 1.2, 1.5 degrees. However, when it comes to, or with greenery and combination of a reflective material with a peak reduction of a couple of degrees, 2.3. However, we did not have enough benchmarks to test if the climate models can reliably reproduce the synergies between heat mitigation technologies. So this is still one of the areas where there's some science to be developed still, and we need to improve the performance of models to prevent performance gap and underestimation or overestimation of the effects. Some of the limitations of climate modeling practice when it comes to trees. So like the representation of stem-level conductance and the general representation of latent heat exchanges, plus the overall uncertainty in tree crown and foliage density, which is almost unsolvable issue, because we will never know what is the real transmissivity of the crowns for every single tree that we have around. This is for a tree in a moment in time. Then when we move to heat stress condition during heat waves, we have photosynthesis reduced. We have an increase in photooxidative stress, and leaves get dropped by the trees, and also we have a decrease in the growth rate of the remaining leaves. So these people performed an experiment putting some trees fundamentally in an oven in a climate chamber, and exposing them for different durations of time at different temperatures. And with the very high temperatures, even a very short exposure of less than 20 minutes can cause a loss of foliage by more than 50%. Those are not unheard temperatures, especially in Western Sydney, where for a few hours a year we reach 45 degrees or even 50 degrees in some areas, and it will be more and more frequent in the future. So the information on the performance and the sensitivity of greenery to extreme heat temperatures will be vital to understand whether there will be a widespread failure of the green infrastructure during an extreme heat event or not. So we're not talking, again, like for the curves, we were talking about drops in performance by 20% more. Here, likewise, we're not talking about 1%, 2%, who cares? No, we're talking about qualitatively different. And we can also observe them in the field, looking around with effects of drought and heat wave conditions on trees, leading to foliage damage. okay, they drop the leaves, therefore they're not so they fundamentally behave like in winter. They're not providing shading anymore, or the shading is greatly reduced by this tree. But also, water stress plants do not cool because they have a leaf surface temperatures even 6 to 8 degrees hotter than well irrigated plants, and the overall transpiration is greatly impaired. In general, when it comes to trees during heat waves, there are some conflicting perspectives. So this is one of the areas where a lot of the science is moving. So some species are producing a reaction that can contrast the thermal damage of extreme heat. This is unclear in the literature, and there appears to be some sort of adaptation. However, the dynamic of this phenomenon, of these adaptation phenomena, is still being investigated. What we know is that, of course, then if the extreme heat is sudden and the species do not have time to adapt, therefore we have a dropping of the leaves, and also without irrigation, the mitigation performance is greatly reduced. And here I'm showing climate modeling considering irrigated and non-irrigated trees in a normal situation with a temperature difference at 2 meters height. So with the non-irrigated trees, we have in air temperatures which is 0.5, 0.6 degrees higher during a normal summer period, but during a heat wave, the difference exceeds 1 degree for several hours during the daytime. So the maximum temperature decrease caused by irrigation is 1.4 degrees, but then therefore if we have drought, we do not have irrigation, then we have a substantial performance loss. And here we can see a practical example with after a field campaign supported by City of Parramatta that we ran a few years ago, and we see here a sports field, well irrigated, very cool, surface temperature below 37, 39 degrees, and instead here we see some roofs that are hot, some that are dark and solar absorptive, but also a portion of grass and greenery that is instead very hot because it's non-irrigated and all the grass is depleted here, and it can be as hot as concrete. So saying, okay, we mitigate with this technology or with cool materials or with greenery, if we do not care about the performance of the materials that we are selecting, and then we do not care about the quality and the performance and the maintenance of greenery, is futile. And likewise, it happens for green roofing. And here is an example of a green roof with insufficient storage layer, leading to surface temperature as high as exceeding 40 degrees and way higher than the ambient temperature, and needing constant watering. Therefore, not all green roofs are created equal, and we have a different performance depending on the green roof. So this is one of the reasons why it is important to have information about the performance. Otherwise, if we just use lead protocols that give 1 point in heat element mitigation tick, whatever the green roof is, we're missing an important aspect concerning the real performance in the field of what we are deploying. Likewise, for hydroponic walls, again, they work well when they are very well irrigated. So here you see the different surface temperatures of a hydroponic wall when it's irrigated, and for another wall next to it with comparable solar reflectance, so lower than 0.4 degrees, which was 14 degrees high in surface temperature. However, if we have a drop in irrigation, we have a completely different situation. One of the aspects that greatly determines the size of the crown of trees is how well they can grow, and if they have available soil for the growth of for the growth of healthy roots. So if they're planted just in a car park without a structured soil, like in many car parks, after 15 years, it's still not providing a lot of shade, and instead with a structural soil with a more efficient technique to allow for the roots to grow well, we have a completely different performance. So the difference is staggering here. They have a very different growth rate, a different size of the canopy, plus all the other aspects concerning removal of pollutants and maintenance costs and so on and so forth. But however, the performance in the field is largely influenced by the installation. So this was, we discussed about cool materials, then we discussed about greenery, and then I mentioned that water misting is just some technical failure of the nozzles, which are getting clogged. Therefore, we're not discussing it here today. The other aspect that is often mentioned is an approach to mitigate urban overheating is a reduction of anthropogenic heat emissions. So the heat exhaust from condensing units. So during heat waves, we have a peak in electricity demand. As you see here, when we have the peak in temperature, you have also a peak in power demand. This is across New South Wales. And however, when we have an increase in ambient temperature, the COP of all thermal machines drops, and therefore they cool the indoor temperatures less effectively, so they're less efficient. But also it means that they are releasing more heat in the built environment because they are used for longer, they're running for longer, and they are not making it to the efficiency is greatly reduced. So as a result, they fail us when we need them the most. Especially when they are behind louvers, so it largely depends on the conditions, and also when the installation conditions are silly, like the ones that we see here, that are real, they're not photoshopped, but some people thought it was a good idea to have this. I have no idea what the COP or the ER of these might be. So to recap on heat mitigation, so with crops and shade trees, we are reducing the air conditioning uses, and therefore we are reducing the demand of power plants. These are the direct effect on energy. And then the indirects are that we are reducing outdoor temperature, and we are also mitigating the built environment and also consequently reducing pollution. We might think that what about compound crisis? Will not all fail at the same time? Well, actually, yes, we had a compound crisis. We have heat waves with bushfire. And this is one of the challenges. So if we have drought, we have a dry soil. If we have dry soil, we result in bushfire. If we have bushfire, we have a smoke, and it gets into poor air quality, but also it gets on soot on cool roofing, and soot also on greenery. We cannot open the windows because we have poor air quality, and we cannot use natural ventilation. This is gone. And therefore our adaptation capacity is compromised. If we have soot on roofing, our mitigation capacity is compromised. Again, if we have dry soil, again, we have extreme heat. it's when you usually have extreme heat, we have also low relative humidity. We have reduced evapotranspiration, therefore the greenery is less effective. When we have extreme heat, we have higher temperatures, and also the COP of HVAC drops, and the yield of photovoltaics drop. Therefore, we're using more electricity from the grid, and PV also it's producing less electricity, meaning it's releasing more heat into the urban environment because it's transforming less sunlight into electricity and more into heat. So therefore, because of these two, we have an increase in anthropogenic heat. So as we see here, and as a result of this, we have an increased electricity demand because of these two. So it's very much linked. So it's it's a substantial chain of events that it's difficult to predict. Then we might say, what about the flood conditions? It's not antithetic. So all we said so far is not antithetic, because the urban heat mitigation and the management of the other side of blue and green infrastructure, they are not competitors, but they should work in synergy as much as possible. So to conclude, heat mitigation technologies suffer performance losses. They can be substantial, like any machine, like anything. They should be accounted for, and there's a need for structured data and metadata. And the new generation of models should be able to represent these synergies and compound crises, because that's very important to understand what happens. And compound crises do occur, like the cold snapping in Texas in February 2021, or the bushfire season coupled with some heat waves in 2020 in Australia. So some reflection. We need pilots, we need installation, we need to fail ASAP, because if we don't fail now, we cannot afford to fail in 2050. We need to fail now and learn from failures in the implementation. Because from science to engineering, then to implementation doesn't happen overnight. And there's an analogy. So after the oil embargo in the 1970s and 73, a lot has been done on the science side, and in International Energy Agency, the word was energy conservation, and also the symbol was a house with a scarf around. So all the science about thermal insulation was well known. However, the real implementation took some time, and then in the early stages of implementation, okay, there were not controls, people were not actually putting the thermal insulation, and then there was performance gap and so on and so forth. It took quite some time to get to actual delivered performance. So we have the science about heat mitigation. We needed to care about the implementation. This said, just take a couple more minutes to say for a few announcements. So we have a recent paper published on the energy impact of coal roofs in Australia. The links are provided here. And also there's another paper about the integrated assessment of urban heating and the impacts on human life. This is open source. And also we have a book that has been recently published. So the first edition is out now, and you can check it out. Thank you for your attention, and we can discuss and can address your questions now. Thanks.
Thanks, Dr. Riccardo, very much for your scientific and a wonderful talk. We move to question and answer session. If you have any questions, could you please put in the chat? Also, we have received one question during the registration process. Over to you, Riccardo.
Thank you.
Riccardo, can you start?
I'm here.
Yeah. Can you answer the question we received during the registration process?
So can you remind me the question, please? So I'm sure
Oh,
it was about
sure.
trees.
Yes, yes. Thank you. I have a question on measuring urban tree cover. Our city council has data to say they have 50.44% tree cover. However, this of course changes suburb to suburb. What is the best strategy distribution of tree cover, and how can we ensure we have good measures?
Okay, thanks. So my general response to this is to have trees where they can grow well. So where you actually have the space for them, where you have the space for the roots. Otherwise, their crown will be will not develop well. So other than targeting an absolute number of a theoretical increasing in tree canopy cover, so often that is a metric that is used by councils. So we want to increase the canopy cover from 25% or 14% in some areas to 40%, or they have to wish to the wish to achieve that threshold, because it's easier to of course to measure, because you can take satellite imagery and you can measure that. However, that doesn't tell you anything about, and I'm not blaming councils at all. I mean, that's an easy metric, and that's what I would probably do in the first place. However, that doesn't tell you anything about the mitigation performance. That doesn't tell you how those trees are working, if they are healthy, if they're developing working roots, if they're developing a good crown, and if they are exposed to drought. So my recommendation in that respect is to have at least a filter on the installation conditions. So have a threshold, or have some boundaries on set some boundaries on what are the installation conditions, whether you can actually provide irrigation, whether they can actually work. And then after that, of course, if it comes down to what they are mitigating, whether do they provide the most benefit, whether they are shading more solar absorptive surfaces, they're achieving, of course, the most significant effects, or whether it is possible to achieve that. Then I have a few questions from Zuping Ling. In the future, the roof with solar panel or with roof, any trade-off there, any suggestion? So we addressed this in another webinar. I will keep it relatively short. So the PV panels, of course, produce electricity, but only a fraction of sunlight is converted into electricity, on average between 10 to 15%, or average over the hours of sunlight. So it is not like the peak production that you have over just a few hours in peak conditions. When you have especially heat waves, the air temperature increases, and the yield of PV, the production of electricity, the efficiency decreases, and therefore they release more heat. In general, PV panels release heat in the built environment. So if you have a built environment which is already overheated, perhaps it would be best to have racks on a solar farm out of the city, so not having on-site PV. But that is a planning decision, and in the long run, the best outcome would be to have a new generation of photovoltaics that convert solar energy convert sunlight into electricity, into solar energy over the entire solar spectrum, so not releasing so much heat in the built environment. So that is the thing. Then there's another question. So I'm sorry to know your name, BN Zirel. In terms of climate change resilience, what would you agree that biosolar roofs, green roofs with solar panels provide more benefits when combined as green roofs? So keep solar panels cooler, and solar panels increase shade and plant diversity. Yes, of course, green roofing decrease the temperatures, and therefore they're helping a little bit the PV panels by reducing the temperatures. However, how much, that's another story. As I've shown before, the performance of green roofing is highly variable, and it changes significantly over time. So it's not a plug and play technology. It takes a lot of care in this selection and installation. So the uncertainty part there is not related to the PV panel, because the performance of PV panel is known. The uncertainty component is connected to the green roofing. And I had monitored green roofing for a number of years in Europe, and was involved in comparisons with green roofing in Germany, in Italy, and in Malta, so across European climates, and also in Portugal. And the performance was, even for the same type of green roof, was largely variable. So it's a living thing. So that is the thing. So it cannot be tested in the laboratory. Then there's a question by Noni. With the NCC 2019 Volume 1, there's a deemed to satisfy provision of solar absorbance not exceeding 45%. Over time, these buildings will have a solar absorbance of 0.6, 0.7 or more. Should maintenance be informed in the planning system to maintain a better solar absorbance while buildings age? For cleaning, there are a few papers about cleaning of co-roofing. One by Levinson and others of 2005. Okay, not the whole performance is recovered only when you bleach them, which is not environmentally awesome. However, then the performance drops again. So my perspective on the topic is that cleaning has a substantial cost, a substantial environmental impact, and the cleaning just with water, with rinsing, is not effective in recovering performance. I've tested it on roofing materials, on facade also, and so the only thing and the easiest thing, in my opinion, is the selection of materials, so that you have materials. Do some things that are very, very simple, not go for anything super complicated, but have a minimum slope. For instance, if you're talking about a regulatory perspective, to preserve reflectance, the slope is the single most important factor, more than anything else. So titanium dioxide self-cleaning and things will not be forever. The slope is forever. In the NCC, you have a minimum fall of 1:80. Which is less than the 2% that is required by standards in Switzerland and in Italy. So the slope is the single most important factor that contributes to accumulation of dust, and therefore a reduction in the runoff and natural self-cleaning. Okay, so the slope is one. And then the second one is having relatively smooth surfaces, so nothing really complicated. These are some of the factors that can limit the performance loss to 0.1%. Sorry, 0.1, namely 10% from 80%. This is the case, for instance, for metal roofing. Often metal roofing preserves very well the initial solar reflectance because of this combination of factors.
Thanks, Riccardo. There is one more question at the beginning.
So there's one question.
Yeah, if you were going to make recommendations for new planning rules, what would they be?
For planning rules would be to go towards monitoring. So like for buildings, having monitoring of implementation. So so not just a general implementation of heat mitigation, but embeds the monitoring part in the continuous commissioning, like it's done for buildings. So the post-occupancy evaluation also for heat mitigation, because that is the single factor that helps to have a continuous improvement. And then aside from what happens, maybe in some area, you'll from this monitoring, you will learn that what is really important is this factor to contrast the performance loss. In some other area, there might be something else. So it's not, I understand it's not a direct response, so it's an indirect one, but the measurements and the monitoring are very important.
Thanks, Dr. Riccardo, very much. Also, thank you so much for joining us today. This is the last high performance architecture webinar this year. Thank you so much for making this webinar series a great success. We look forward to seeing you next year. Bye.
Thank you, Lan. Thank you, everyone.